Welcome, and thank you for choosing to attend NGA's Understanding Applications for Heat-Treated Glass presentation. The National Glass Association is a registered provider with AIA. Following this presentation, you'll be directed to complete a brief quiz to ensure your understanding of the presentation's learning objectives. By the conclusion of this presentation, you'll be able to state the two main reasons for heat-treating glass, describe the differences in characteristics between fully tempered glass and heat-strengthened glass, list two typical applications for fully tempered glass, and explain the three phases of heat-treating glass. Heat-treating glass increases the strength of glass. Compared to annealed glass, heat treating increases the strength of heat-strengthened glass by up to a factor of 2, and tempered glass by a factor of 4. Ever-increasing strength requirements have increased the need for heat-treated glass. Tempered glass not only provides a significant increase in glass strength, but is also a safety glazing material when it meets a safety glass standard. Because tempered glass breaks into small particles, it significantly reduces the risk for injury from impact. If there are concerns from glass fallout, laminated glass or a tempered laminate may be used. The most commonly used process for heat-treating architectural products calls for the glass to be cut to the desired size, transported through a furnace, and uniformly heated to approximately 1150 degrees Fahrenheit. Upon exiting the furnace, the glass is rapidly cooled by blowing air uniformly onto both surfaces simultaneously. This process is known as quenching. The cooling process locks the surfaces of the glass in a state of high compression, and the central core in compensating tension. The two types of heat-treated glass include fully tempered glass and heat-strengthened glass. The primary difference comes with the resulting surface compression upon heat treatment. Fully tempered glass must achieve one of three stipulations: have a minimum surface compression of 10,000 psi, or an edge compression not less than 9,700 psi, or meet the requirements outlined in the Voluntary Safety Standard ANSI Z97.1. Heat-strengthened glass must have a surface compression between 3,500 and 7,500 psi. The definitions for fully tempered glass are those used in ASTM C1048, the industry standard for definitions of fully tempered and heat-strengthened glass. The higher compression levels required for fully tempered glass yield a product that is generally 4 times stronger than annealed glass, and twice as strong as heat-strengthened glass, of the same thickness, size, and type. When broken by impact, fully tempered glass immediately shatters into relatively small pieces, thereby greatly reducing the likelihood of serious cutting or piercing injuries in comparison with ordinary annealed glass. To qualify as a safety glazing material as defined by ANSI Z97.1 and CPSC 16 CFR 1201, the 10 largest particles taken from a broken fully tempered light of glass weigh no more than the equivalent weight of 10 square inches of the original specimen when tested according to the standards. Heat-strengthened glass is produced with surface and edge compression levels less than fully tempered glass, as specified by ASTM C1048. The lower compression levels yield a product that is generally twice as strong as annealed glass of the same thickness, size, and type. Heat-strengthened glass with low compression levels will tend to fracture into large fragments, similar to annealed glass breakage. As the compression levels increase, the size of the particles of broken glass tend to become smaller. Due to the nature of its treatment, heat-strengthened glass does not meet the safety glazing requirements of ANSI Z97.1. The specific break pattern of heat-strengthened glass is preferable for some applications. If it meets all requirements, codes, and specifications, heat-strengthened glass should be used in all applications where annealed glass will not meet thermal or wind load requirements. Heat-strengthened glass is also the recommended choice for spandrel applications. These photos represent the different break patterns that could result upon use of either heat-strengthened glass, which has lower compression levels, and fully tempered glass, which has higher compression levels that qualify for safety glazing applications. The characteristics of heat-treated glass that are unchanged by heat treating include the glass properties, glass fabrication, optical properties, and glass surface. For additional information on these properties, contact your glass manufacturer or fabricator. Examples of glass properties that are unchanged by heat treatment include color, deflection, emissivity, reflectance, and more. There are certain do's and don'ts when dealing with heat-treated glass. Because heat-treated glass has significant internal stresses, post-fabrication procedures can result in breakage or weakening of the glass. For instance, heat-treated glass cannot be cut or drilled post-treatment. Edging and etching also impact the strength of glass. See NGA's Glass Informational Bulletin, The Importance of Fabrication Prior to Heat Treatment for details. Another important characteristic of heat-treated glass is its optical properties. Residual stresses induced by the high heating and rapid cooling cycle can result in surface deformations, such as bow, sometimes called warp, and roller wave. The former is caused by non-uniform stresses in the glass that can result in an edge-to-edge curl, or smaller localized depressions. The latter is a repetitive wave-like departure from flatness related to a horizontal conveyance system, heat treating process, excluding edge effects, and distortion influenced by assembly or installation. These deformations can cause aesthetic issues, such as undesirable reflections. While difficult to eliminate completely, these generally undesirable effects can be controlled and minimized with proper attention to furnace maintenance, loading practices, and quality control procedures. Under certain conditions, the residual stress in the glass may become visible. This strain pattern effect, also called iridescence, is more noticeable in outdoor and automotive glasses at certain times of the day and viewing angles. Obviously, IG and laminated units that consist of multiple lights of heat-treated glass will have a tendency to magnify these undesirable optical properties if present, but it's important to note that roll wave and iridescence are strictly aesthetic issues that do not affect product performance. Other intrinsic surface characteristics seen in heat-treated glass that do not affect performance may not even be visible to the naked eye under normal viewing conditions. These include microscopic soot and other fine particles embedded in the glass surface from the manufacturing process, and small irregularities due to roller pressure. A certain level of these unavoidable blemishes are allowable under ASTM and other industry standards, as are inherent irregularities in the glass composition itself that can also contribute to optical distortion. While heat-treated glass is very strong because of the high compressive stress developed at its surface, it will break when that surface compression is breached, either from within or without. The majority of heat-treated glass spontaneous breakages are from one or a combination of the following causes. 1. Surface or edge damage. 2. Deep scratches or gouges. 3. Severe weld splatter. 4. Missile or wind-borne debris impact. 5. Glass-to-metal contact. 6. Wind and thermal loading. And 7. Inclusions. In the manufacturing of float glass, impurities may be introduced into the molten glass. Most of these cause no particular problem. According to ASTM C1036, they are defined as a form of gaseous or crystalline or stone blemish. The specification offers test methods for detection as well as more information on size and frequency. In most cases, inclusions do not affect glass performance or cause glass breakage. In the manufacturing of float glass, impurities may be introduced into the molten glass. Most of these cause no particular problem. According to ASTM C1036, they are defined as a form of gaseous or crystalline or stone blemish. The specification offers test methods for detection as well as more information on size and frequency. In most cases, inclusions do not affect glass performance or cause glass breakage. As mentioned, there are various types of inclusions present in heat-treated glass, and most do not pose a risk of breakage or have any effect on performance. One exception is nickel sulfide inclusions. Nickel sulfide inclusions may be formed whenever nickel-rich contaminants, such as stainless steel and nichrome wire, are unintentionally introduced into the glass melting furnace along with the desired materials. The nickel may combine with sulfur in the furnace fuel, or the batch materials to form nickel sulfide inclusions. In annealed glass, these are harmless and are considered on the same basis as all other inclusions. However, during the processing of fully tempered glass, the nickel sulfide inclusions are transformed into a state wherein they will expand irreversibly with time and temperature. If the inclusion is tightly held in the glass and not otherwise surrounded by a bubble, the expansion may produce enough stress to cause spontaneous glass breakage at a later point in time. The fracture caused by the expansion of the inclusion is quickly propagated in fully tempered glass because of the high tensile stresses inherent in the thickness in the center of the glass. Fully tempered glass, which for quick review has been treated at high compression levels and may be used for safety glazing applications due to its small pebble-like break pattern, may be used specifically in architectural applications that encounter frequent human contact. This may include shower enclosures, glass railings, and those which require protection from natural or man-made events such as hurricanes or force entry situations. Other applications for fully tempered glass include light fixtures, kitchen appliances, and furniture, such as glass tabletops. Transportation vehicles and sports vehicles are also candidates for fully tempered glass thanks to its small break pattern. Heat-strengthened glass will break similarly to annealed glass but offers high thermal and wind load resistance. The glass break pattern will typically prevent glass fallout because the edges will be held in place by the sealants, gaskets, and glazing material. Color, clarity, chemical composition, and light transmission characteristics of glass remain unchanged after heat treating. Solar and decorative applications work well with heat-strengthened glass products. Because tinting reduces the solar transmittance of glass and increases solar heat absorption, heat strengthening is sometimes required due to the heat buildup and resulting thermal stresses. The most commonly used process for heat treating architectural products calls for glass to be cut to the desired size, transported through a furnace, and uniformly heated, then rapidly cooled by blowing air uniformly onto both surfaces simultaneously. Testing and inspection include specific visual inspection criteria as outlined in ASTM C1036, and for fully tempered glass, completing the safety glazing testing criteria outlined in ANSI Z97.1. Before the heat treating process can begin, annealed glass must be cut to the finished size or a processing size for further fabrication, such as polished edges. Glass is typically cut on line by a cutting line as shown on the right, or cut manually with a hand cutter as shown on the left. Typical pre-processing steps, holes, notches, and V-grooving are performed after the glass has been cut to size. Holes and notches can be accomplished with manual or automated equipment. V-grooving is accomplished on automated equipment only. As you can see by the illustration, almost any combination of this type of fabrication can be accomplished. ASTM C1048 describes limits on glass fabrication that can be tempered. These images depict the variety of edge finishing that can be applied to the glass before the heat treating process is begun. Edge finishes are often described as ground, smoothed, or polished. Ground edges exhibit fine linear abrasion marks and a rough appearance. Smoothed edges have a frosted appearance that diffuses reflected light. Polished edges are reflective in appearance, similar to the major surface of a glass light. Decorative treatments, such as edging or sandblasting, should also occur prior to heat treatment. The identification marking, when required, shall include the manufacturer's name or trademark, the designation of heat-strengthened or fully tempered, and glass thickness. These logos can be sandblasted, silk-screened, etched, or applied by laser. Ensuring the glass is as clean as possible prior to fabrication is imperative. These photos illustrate glass going through a washer prior to fabrication. Once pre-processing is completed, the glass is ready for the tempering furnace. There are a variety of furnaces available for heat treating flat glass, ranging from small batch to large continuous feed systems, with many features designed to ensure high yield and throughput. However, the basic process has not changed much over the years. As this video from Glaston shows, newer tempering furnaces use convection to heat high-performance low-E glass more quickly and evenly. After the glass has gone through the washer and is dried, it's ready to enter the oven or furnace to be heated before entering the cooling or quenching phase, which locks the surface of the glass in a state of high compression. Quality control of heat-treated glass is critically important in order to ensure compliance with industry standards, as well as the requirements of specifiers and end users. There are several instruments and test methods available to fabricators for monitoring optical quality. These include the basic Zebra board, which is mounted over the exit of the tempering furnace, allowing a trained operator to recognize undesirable reflective distortions, and manual gauges that detect and measure the repetitive cylindrical deformations in the glass surface that can cause so-called roll wave distortions. There are also online or offline PC-based instruments that use digital photography of reflected reference grids or rasters, and specialized software to measure and report not only roll wave, but other surface deformations as well. The center punch fragmentation test method was developed by the Glass Association of North America, now combined with NGA, in 2004. It is known as GANA 101-04. Standard test method for center punch fragmentation of fully tempered flat glass. This test method covers the destructive fragmentation and evaluation of the fracture pattern of monolithic fully tempered flat glass products intended for use in architectural safety glazing applications. This test method is intended for use as an in-plant quality control test to evaluate the fracture pattern of fully tempered glass. This test method is not a substitute for safety glazing test requirements of ANSI Z97.1 or CPSC 16 CFR 1201. This video shows the center punch fragmentation procedure. The impact test determines the foot-pound impact the glazing can withstand when impacted at different heights and producing an acceptable break pattern as outlined in the code. To successfully pass the impact test, ANSI Z97.1 states that no tear or shear or opening will develop through which a 3-inch diameter sphere can pass freely. Measurement devices for edge and surface stress are additional tools that may be employed that will not destroy the sample light being tested. Throughout this presentation, we've discussed a number of areas surrounding heat-treated glass. You should now be able to state the two main reasons for heat treating glass. Describe the differences in characteristics between fully tempered glass and heat-strengthened glass. List 2 typical applications for fully tempered glass. And explain the 3 phases of heat treating glass. Thank you again for attending Understanding Applications for Heat-Treated Glass. We hope this continuing education program was helpful in bringing you up to date on the capabilities of heat-treated glass. Please click Next to be taken to the questionnaire, which will allow you to complete this course.